Okay, I wanted to set up just one simple example that I didn't get to on Monday in lecture. I shouldn't say simple example, but it's a kind of fun, interesting example. And that's the case of a water droplet. It's going to be very similar to the bubble problem that you work in the homework. But I'm going to think here of a droplet that's spherical, where we have water on the inside and air on the outside. And the pressure inside that droplet is, say, P1, and the pressure outside is P2. Now, if P2 is greater than P1, clearly I think everyone would understand that the droplet would collapse. It would be basically compressed under the pressure differential. Even if P1 and P2 were equal, the droplet would collapse because surface tension is acting to constrict this spherical droplet. So we have that P1 is greater than P2. Now what I'd like to pose is, how do we figure out by how much? By how much more is P1 greater than, how much more than P2 is P1? Let me just try to say it more clearly. So by how much is P1 greater than P2? Well, what we'd like to do is set up a force balance for this droplet, but unfortunately, if we look at this spherical droplet in total, the pressure differential is acting radially outwards everywhere, and this is not great radial drawings, but you get the idea, that it's pressing out radially every which way. And so if we do the force balance for the entire sphere, the pressure itself cancels out with the upwards forces and the downwards forces, say, canceling one another. So to really get at the dynamics that's maintaining this droplet, we need to think of half of the droplet. So here I sketch half of the droplet, a semisphere, a hemisphere, and now we can think about the forces that are acting on the droplet. So we have the pressure acting radially outwards from this hemisphere. Now what we want to do is think about the component of that force that's acting in, let's say, the x direction, because where's surface tension acting in this diagram? And I'll sketch the surface tension in black. The surface tension is acting all around the air-water interface, around the circumference of the hemisphere. And so we have this surface tension that's pulling to the left and pressure that's pushing outwards to the right. Now we can go through and do a whole formal integration of the pressure, taking the component of the pressure that's in the x direction. But I'm going to just note that the total pressure force, F sub P, is equal to P1 minus P2 times the area, which is going to be pi r squared. We'll prove that more later when we get into integrating pressures to define forces. The surface tension, call that F sub sigma. F sub sigma is equal to the surface tension coefficient sigma times the length over which that force acts, which, as we said, is the circumference. So that's 2 pi times r. If we're in an equilibrium, then let me write out equilibrium. That is, the droplet is being maintained at a steady radius. Then we can say that F sigma has to equal Fp. And equating those allows us to say sigma times 2 pi r, the surface tension force, is equal to the pressure differential P1 minus P2 times pi r squared, or P1 minus P2 is equal to 2 sigma over r. Again, very similar to the bubble case that you're going to be working on the problem set this week. Important to note that the bubble has two interfaces, on the inside and the outside, so the analysis will need to be modified accordingly. Good luck.